Hi class. In this lecture here, what we want to do is we want to talk about methods for evaluating limits analytically. So what we've done in the previous lectures is we've kind of looked at like the concepts of limits. We talked about methods for solving limits using a table of values. It was very arduous. And then we talked about methods of evaluating limits by looking at the graphs. And that wasn't too bad. But so in this section here, what I want to do is I want to show you how different methods, different approaches for evaluating limits. So ones that won't involve a table or necessarily looking at their graphs. So here are going to be the methods we're going to discuss today. We're going to evaluate a limit using the property of limits. We're going to developing and using a strategy for finding limits. We're going to be talking about evaluating a limit using the dividing out technique. We're going to talk about evaluating a limit using the rationalizing technique. Then we'll talk about something called the Squeeze Theorem. And then actually at the end, what we're also going to do, a little bit extra, we're going to look at some special trig limits. And those are quite fun. All right, so this lecture is going to be a rather lengthy lecture. So there's going to be a lot of stuff I'm going to talk about, and it's going to be filled with a ton of examples today. So what I suggest you do as you watch this lecture is download my lecture and take notes as I go through with this. Also, when you see me write a problem, what you might also want to do is pause the lecture and see if you can solve this on your own without my help, and then unpause the video and watch me do it and see if you get the same answer. Okay, so let's jump right into it. Okay, so let's talk about some basic limit laws here. Okay, so first off here, if b and c are real numbers, okay, and let n be a positive integer, we have the following. Okay, so b is a real number here. So the limit as x goes to c of a real number, it's just so think about this as a constant, is just the constant. So for example here, if I say what is the limit as x goes to 3 of the number 5? Well, look what's going on here, right? So what we're saying here is my function f of x is equal to 5. So if you were to just look at that, right, like look at the graph of this, it would just be a horizontal line. So if here is 3, as x goes to 3, you're just staying at the constant value. It's 5. Okay, and it holds for anything. Okay, so for example, if I say the limit as x goes to 2 of a constant, even the number e, right? This is just still e, right? Or the limit as x goes to negative 3/4 of the number 7. All right, whatever. If it's just a constant, the limit as x goes to some real number itself is just the constant right here. Here, the limit as x goes to c of just x, okay, that's equal to c. So for example, if I say the limit as x goes to 2 of x, well, if you were to sketch the function f of x is equal to x, it would just be a straight line like this. And so as x goes to 2, you would also see it would just go to 2 here. So if it's just the x, just x by itself, you literally just plug whatever number in, and that would be 2. So for example, if you had the limit as x goes to 4 of x, that's just 4. You're literally just plugging it in. And then as long as this n is a positive integer, right? If you have the limit as x goes to c of x to the n, you're literally just going to plug c in here. So for example, if you have the limit as x goes to 2 of x squared, that's just 2 squared, that would be 4, okay? Or if you had the limit as x goes to negative 2 or negative 2 of x cubed, well, that would be negative 2 to the 3rd power, which gets you negative 8. So you could literally, what you're doing here is you're just plugging it in. So for these two, you're just plugging in for x. Literally, that's what you're doing here. Okay, so these are very, very straightforward limits to solve here. Next, we have just some properties of limits. So here, let's let b and c be real numbers, and again, let n be a positive integer. And let's let f and g be functions with the following limits. So the limit as x goes to c of f of x is equal to L, and the limit as x goes to c of g of x is equal to k. So what the big takeaway here is both these limits exist. So as long as both these limits exist, okay, so these properties fail if one of the limits does not exist. So both these limits need to exist. So if the limit as x goes to c of some, constant times a function, really what you're seeing here is you can, if it helps to see it this way, you could factor this out, right? So this becomes b times the limit as x goes to c of f of x. Or here, if you have the limit as x goes to c of two different functions, really what's going on here is you have the limit as x goes to c of adding and subtracting of two different functions of f of x plus or minus the limit as x goes to c of g of x. So you can evaluate the two limits separately. Here, if you're multiplying and both the limits exist, you have the limit as x goes to c of f of x times the limit as x goes to c of g of x. Okay, so you can just, figure out the limits separately and multiply them if that helps. Here, okay, you have what looks like a rational expression, but it could be anything. Okay, so these are just two functions here. All right, so as long as k doesn't equal 0, because you can't have a 0 in the denominator here, you have the limit that you could evaluate this as the limit as x goes to c of f of x divided by the limit as x goes to c of g of x. And if you have the limit of f of x raised to the nth power, so if this would be some constant like 2 or 3, something like that here. I'm going to move this over here. So a little bit cut off here, sorry about that. You can evaluate this as the limit as x goes to c of f of x, and then take it to whatever power. Okay, so you would do it that way. So these are all just limits that you can use to, or properties, excuse me, that you can use to help you evaluate limits. And you're going to see in the coming examples how all of these are going to come into play here. All right, next we have polynomial and rational functions. These are going to come up a lot, and they're really, really easy. So if p is a polynomial function and c is any real number, okay, if you have the limit as x goes to c of p of x, all right, you just evaluate this at p of c. So what you're doing here, notice, all right, as long as it's a polynomial, okay, and I'm asking you to find the limit as x goes to c, you're literally just plugging c into f of x. That's it. That's all you're doing. Piece of cake, okay, as long as it's a polynomial function. Now, if it's a rational function, okay, so it's given by the rational function is equal to p of x divided by q of x. So it's the division of two polynomial functions itself here. And c is a real number such that you can't have the denominator equal 0. Okay, remember, can never divide by 0. If I have the limit as x goes to c of r of x, again, you're just plugging c into the rational function. All right, as long as it doesn't make the denominator equal 0. So we're going to talk about some cases later on in the lecture when you do have a rational function and you get to divide by 0, like what happens. Okay, sometimes you can evaluate that limit with some tricks, and that's what I'm going to show you later on in this lecture. Okay, so here's the big ones. Okay, what we've done so far: constant. Piece of cake. Limit as x goes to c of any constant is just the constant. If it's x, limit as x goes to c, just plug it in. If it's x to the n, again, this is just a polynomial function, right? So you're literally just plugging c in. All right, polynomial function, plug it in. Rational function, plug it in, literally as long as it doesn't make the denominator go to 0. Okay. So let me show you this one. So consider this function, why this works. Okay. Let's look at f of x is equal to x squared minus 4. All right, so look at the graph over here. So The y-intercept is -4. 2 and -2 are the x-intercepts, right? And so if you plug in 3, you get 9. 9 minus 4 is 5. And this is what this graph looks like here. It just looks like something like this, okay? If I say what is the limit as x goes to 2 of f of x. Okay, if you just look at the graph, look, as x goes to 2, what is happening? All right, the value of the function, it's going to the value 0, the y value is 0, right? And you can see this similarly because it's a polynomial function. Okay, because it's a polynomial function, literally what you could do is you can just plug in x is equal to 2 into the function. Okay, so look, the limit as x goes to 2 of f of x is the limit as x goes to 2 of this x squared minus 4. So because it's a polynomial function, literally you're just plugging it in. So this becomes 2 squared minus 4. It's me 4 minus 4 gets me 0. Okay, so just the big takeaway here is that whenever it's a polynomial function, whoop, whoop, I just plug it in. You got a little crazy sound effect there, but you just plug it right in. All right, let's work some other examples here. So you just without the graph, so you can just see it plugging it in. All right, so let's do this example here. Let's do the limit as x goes to 2 of 3x squared minus 5. Well, look, because it is a polynomial function, you're literally just going to plug this 2 in. So you get 3 times 2 squared minus 5. So what is 2 squared? 2 squared is 4. 3 times 4 gets me 12. Right? And then 12 minus 5 gets me 7. So I literally just plug this in. Let's try this one. The limit as x goes to -1 of this, x squared minus 8x plus 2. So ask yourself this, is it a polynomial function? Yes! So literally just take this -1 and plug it in. So -1 squared minus 8 times -1 plus 2. All right, well, -1 squared is 1, right? Negative times negative is a positive. -8 times -1 gets plus 8. And then I have this plus 2. 1 plus 8 is 9. Excuse me. Plus 2 gets me 11. Okay, here's a fun one to try. Okay, and so this is the limit as x goes to 1/2. Okay, so it's going to a fraction. 1/2 of x squared minus 4x plus 1. And what you should do, right? What you should do, just if you're watching this lecture and you've seen me do a bunch, like this is just an algebra problem, but you should probably like pause the video here and see if you can solve the problem. So I'm going to just pause for 1 second, allow you to pause the video and give it a shot, and then unpause and see if we get the same answer. Okay. So hopefully you gave it a shot, but if you just want to watch the video and see how this is solved, let me show you what's going on here. So you're taking this 1/2 and you're plugging it in because it's a polynomial function. So you get 1/2 squared minus 4 times 1/2 and then just plus 1. All right, so 1/2 squared, that gets me 1/4. Minus 4 times 1/2 gets me minus 2 plus 1. Right, then you just need a common denominator, right? So the common denominator here is 4. So it's minus 4 times 8 over 4, because 8 over 4 reduces to 2, plus 4 over 4, right? So look, 1 minus 8 is 7, -7. Negative 7 plus 4, this gets me minus 3/4. Should be my final correct answer here. Okay. So yeah, hopefully not too bad. Just polynomial functions. Just plug it in. Okay, so these were all polynomial functions. All right, now let's go back, and I said also with a rational function, as long as it doesn't make the denominator equal 0, literally you can just plug it in. So let's now do some examples of rational functions, okay? So here'll be the first one. It's just very simple. Look at the limit as x goes to 3 of x plus 5 over, let's look at x squared minus 1. So notice, if you plug 3 in the denominator, you do not get 0. So literally, you're just going to plug this in. This is 3 plus 5 all over 3 squared minus 1. Well, 3 plus 5 gets me 8. 3 squared gets me 9. 9 minus 1 gets me 8. Oh, this is cool. 8 over 8, it just simplifies to 1. Let's look at this one. The limit as x goes to 0 of x squared plus 8x minus 12 all over x squared minus 5x plus 3. Well, look, you can plug 0 in, all right, as long as it doesn't make the denominator equal 0. So which is absolutely the case. Like if you plug 0 into this, you do not get a divide by 0. So this just becomes 0 squared plus 8 times 0 minus 12 all over 0 squared minus 5 times 0 plus 3. Well, look, 0, 0, 0, 0. So this just becomes minus 12 over 3, which is just negative 4. All right, here's an algebraically intense one. Let's look at the limit as x goes to 1/2 of x squared minus 3x all over x plus 1. So again, just to practice your algebra, what I encourage you to do here is I encourage you to pause and give this problem a shot just to see if you could do it. And then let's hopefully you gave it a shot, but if you just want to watch, now let me show you how you do this. So again, you can just plug this right in. So this is 1/2 squared minus 3 times 1/2 all over 1/2 plus 1. Okay, so 1/2 squared is 1/2 times 1/2, so this is 1/4 minus 3 times 1/2 is minus 3/2 all over 1/2 plus 1. So, what is that? So this becomes 1/2 plus 2 over 2. So you need a common denominator in the top, right? So it's 4. So this is 1/4. This becomes minus 6/4 all over here. 1/2 plus 2/2 gets me 3/2. So then look, 1/4 minus 6/4 gets me 5/4. Excuse me, negative 5/4 divided by 3/2. So then I have a fraction divided by a fraction, so this becomes keep, so minus 5/4. Change the division to multiplication, and whoop, flip this. This becomes 2 over 3. So look, now just multiply. So this becomes minus 5 times 2 gets me minus 10. Over 4 times 3 gets me 12, which we very, very quickly see reduces to minus negative 5/6 or negative 5/6 there. So when you have these fraction problems, right, just be meticulous with them, right? Because there's a lot of opportunities to make mistakes. So, just take your time as you approach these problems. Okay, so far they've been pretty straightforward. Just literally just plugging them in, right? So if it's a polynomial function, just plug it right in. If it's a rational function, long as the denominator you don't get to divide by 0, just plug it in, and that's how you can very quickly evaluate the limit. Okay. So now let's look at limits involving a radical. Okay. So let's just let n be a positive integer. Okay, 2, 3, 4, all right, etc. The limit below is valid for c when n is odd. Okay, so any c, so it can be a negative number. And valid for c is greater than 0 when n is even. Okay, right, because you can't have a negative under a square root, right? So the limit as x goes to c of the nth root of x, you can just plug it right in. So again, just plug it right in. All right. Now here's a tricky one. So this is the limit of a composite function, and you'll see this will make more sense after I do the first example here. Okay. If f and g are functions such that the limit as x goes to c of g of x is equal to L. Okay. And then look, this L, the limit as x goes to L of f of x is just f of L. Then you have the following. The limit as x goes to c of f of g of x as a composite function here. Okay. You're gonna evaluate the limit inside first, and then whatever this becomes, okay, as long as is the same thing as x, the limit as x goes to L of f of x, you're just literally gonna plug in L into this and get f of L. This will make again more sense when I get to the next side, but really what's going on here is you're just plugging in. All right, let me give you some examples of this so you can see, okay? So of these radicals and composite functions here, okay? So here'll be the first one. The limit as x goes to 3 of the square root of 3x squared right here. So this is a composite function. So if we let g of x be the inside part and f of x be equal to the square root of x, we see that this right here looks a lot like f of g of x. Okay? So really what you're doing is you're just taking this 3 here and you're just going to plug it in. Okay? As long as you don't violate the domain, like this is an even root, so this has to be positive. The inside, under the radical has to be positive. You can just plug it right in. So this becomes the square root of 3 times 3 squared. Well, 3 squared is 9, so it's the square root of 3 times 9, which is the square root. You could see how to simplify this here, but this is the square root of 27. Or you can take the 9 out as a 3, and it becomes 3 square roots of 3. So again, really the key takeaway here is you're just plugging in. Okay. Let's look at this one right here. Okay. So the limit as x goes to 1 of 3x squared plus 2, and this will be to the third power. Okay. So this, again, is a composite function, right? The f of x would be x cubed, and the g of x would be this 3x squared plus 2. But it's also just a polynomial function here, right? So again, you're just literally going to plug it in. So this becomes 3 times 1 squared plus 2 to the third power. Well, this is 1 times 3 is 3 plus 2. This just becomes 5 cubed, all right, which is just 125 right here. Let's look at this one. Let's look at the limit as x goes to 7 of 3x all over radical square root of x plus 2. Well, look, as long as, literally as long as you can just plug this in and not get it divided by 0, you're just going to plug it in. So this is 3 times 7 all over the square root of 7 plus 2. Well, this is 21 over the square root of 9. Well, this is 21 over 3, which is itself just 7. Let's try this one. let's look at the limit as x goes to 3 of the square root of x plus 3 over x plus 2. Again, you don't get to divide by 0. You don't violate the domain of the square root, so just plug it in. So this is the square root of 3 plus 6 all over 3 plus 2, which is the square root of 9 over 5, which we see is just 3/5. Okay. Let's just take a look at this right here, okay? So this is saying f of x is equal to x plus 7 and g of x is equal to x squared. All right, so let's first find the limit as x goes to -3 of f of x. So literally what you're going to do, okay, what you're literally going to do is you're going to take this -3 and you're going to plug it into f of x. So this is -3 plus 7. This just gets you 4, okay? Now I want to find the limit as x goes to 4 of g of x. Well, g of x is x squared, so this is just 4 squared. Gets me 16. Well, now look what's happening here. I'm asking you to find the limit as x goes to 3 of g of f of x. Well, because this is a composite function, what is the limit as x goes to -3 of f of x? Well, that's 4. So this would just be g of 4. Well, what is g of 4? We just saw that over here, right? Because you just plugged it in. It's just 16. So you can backtrack this and see what you're doing. You really just, literally what you're doing is you're just literally plugging it in. So as long as you can plug the value into the limit, okay, as long as you can plug the value into the limit, just do that, okay? And you'll straight up get the answer. Okay, let's now look at some transcendental functions, including some trig functions here, okay? So let's let C be a real number in the domain, okay? So it has to be in the domain of the given transcendental function, okay? So we remember, right, like tangent, cotangent, secant, and cosecant, right? They have vertical asymptotes in there, right? Like there's numbers not in the domain. So it might help you, okay? So this is just a suggestion. Review the trig functions, okay? Okay, especially their graphs, okay? Right, that's really important here, okay? Because you're going to notice as I go through the lecture in these classes, like I'm just going to assume you remember your trig, okay? Because it's pre-calculus is a prerequisite for this class. So just make sure you have your full understanding of your trigonometric functions and especially even the trigonometric identities. Okay, so really what's going on here, look, as long as C is in the domain of the given transcendental function, okay, as long as it's in the domain, that's important, as long as it's in the domain, really what's going on is you're just plugging x is equal to C into the function. Okay, literally that's what you're doing. So the limit as x goes to C of sine of x, okay, that's just sine of C. Limit as x goes to C of cosine of x, that's cosine of C. Limit as x goes to C of tangent of x, tangent of C, as long as it's in the domain, okay, right? So like the domain of sine and cosine is all real numbers, but that's not the case for the rest of the trigonometric functions. So limit as x goes to C of cotangent of x, cotangent of C. Limit as x goes to C of secant of x, that's just secant of C. Limit as x goes to C of cosecant of x, that's just cosecant of C. Now here we have an exponential function, so limit as x goes to C of a of x. So okay, so a here is, just so we're clear, a is a real number. Okay, so the variable here is the exponent. So this is just a of C. Okay, this is long as a is greater than 0. So you're literally just going to plug it right in. And the limit as x goes to C of the natural log of x is just the natural log of C. Again, as long as C, in this case here, C can't be a negative number, right? Like, the natural log doesn't exist. You can't plug in natural log of -5. You can't figure out what that is. Okay, let's do some of these problems just so we can recall. Okay. So here's just some, this is handy for you. These are some trig identities. Okay, and this is just the graph of sine and cosine, right? So here will be the first one. This will be the limit as x goes to 0 of sine of x. Well, that's just going to be sine of 0. And then look, what is sine of 0? Sine is the red graph here. Sine of 0, when you plug 0 in, you get 0. Let's look at the limit as x goes to 0 of cosine of x. Well, that's just cosine of 0. And look, blue is the cosine graph. Cosine of 0 is 1. Let's look now at the limit. And let's do as theta goes to pi of tangent of theta. Okay, just changing the variable up here. So maybe think back, like, oh, I don't remember my tangent graph. Oh no. Well, look, what is tangent? Tangent is sine over cosine. So this becomes the limit as theta goes to pi of sine of theta over cosine of theta. Well, that would be sine of pi over cosine of pi. Well, look, what is sine of pi? Well, here, red sine graph. Sine of pi is 0. Cosine of pi, cosine is the blue graph. When you get to pi, cosine of pi is -1. Well, 0 divided by -1 is still 0, right? Piece of cake here. Let's try this one. Let's find the limit as x goes to pi over 2 of cosecant of x. Okay. So again, maybe you forgot what cosecant is, off the top of your head. So let me go back here and look. Well, look what this is. This is 1 over sine. So this is limit as x goes to pi over 2 of 1 over sine of x. So now look what happens when you try to plug this in. This becomes 1 over sine of pi over 2. Well, look, what is sine of pi over 2? You just go, the red graph is the sine. Sine of pi over 2, boom, it's 1. So this is 1 over 1. And the answer is just 1, right? All right, let's try some other transcendental functions. So let's look at the limit as x goes to 2 of 3 to the x power. Well, look, I can just plug 2 into this. This just becomes 3 squared, which is 9. So when you can, literally just plug it in. Let's try this one. The limit as x goes to 1 of the natural log of x. Well, plug it in. Natural log of 1. What is that? 0, right? And imagine you don't, even if you forget this, right? You can just on your graph, you could literally plug this in. Here's the natural log function, and you can see oh, okay, I got it. And then let's just try this last one here. Let's look at the limit as x goes to e of the natural log of x. Well, that's just the natural log of e. And we should remember from pre-calculus that that's just very easily 1. Okay, so a lot of limits, a lot of interesting stuff going on here. So what you're seeing here, okay, and this is the big takeaway so far, is if you can just plug it in, right? If you can just plug it into the limit, you should just do that. Okay, you should just plug it right into the limit. Okay, so now what we want to look at is cases where a little bit more advanced methods where it's what if you can't? What happens when you plug it into the function and you get something like a divide by 0? Okay, that's a big issue. So we use this strategy here for finding limits here. Okay, and it's this theorem that talks about functions that agree at all but one point. Okay, so I'm going to read the definition, and it's going to seem a little weird, and then I'm going to show you with an example how this works. Okay, so let's let C be a real number. And let's let these two functions, f of x and g of x, be equal to each other for all x except specifically when x is not equal to c. okay? And this is on some open interval containing C. So everywhere at C, they're equal to each other, but at C, they're just not, okay? If the limit of g of x as x approaches C exists, then the limit of f of x also exists, okay? And we have the following. The limit as x goes to C of f of x is equal to the limit as x goes to C of g of x. So it's kind of like, what is going on here, okay? Let me show you an example, all right? And then this'll all make sense. So let's consider this function. F of x is equal to x squared minus 9 divided by x minus 3. Look, you can see here that x cannot equal 3, okay? So if I ask you to find the limit as x goes to 3 of this, okay, so of f of x, well, you'd get 3 squared minus 9, so you'd get 9 minus 9 over 3 minus 3. You get this thing that looks like 0 over 0. Okay, this is what's called indeterminate form. Okay. So generally when you have something like this 0 divided by 0, it actually means there's something you can do to evaluate the limit. Well, if we look at f of x, right, we recognize that this factors like this. And the graph of f of x, you can cancel these out. F of x looks like the graph of x plus 3, just x cannot equal 3. It cannot equal 3, all right? So look, if you were to graph this, okay, this is f of x. Okay, it would look like this. It would just have a hole in the graph here, all right, when x is equal to 3. And this graph would literally look like this. Okay, if you were to plug this in your calculator, this is literally what you would see. So look, if we sketch the graph of some new function, that's this crossed out method, all right, this canceled out method of just x plus 3. We would see that these two graphs are exactly the same, except at one point. So they agree at all but one point. And look, we can see that the limit as x goes to 3 actually exists, right? So look, the limit as x goes to 3, it looks like it's going to 6, right? So the limit as x goes to 3 of f of x, it actually exists and it's equal to 6. But the way you can find that is, look, if I can cancel these factors out and then I can plug the value into the remaining function, boom. So look, it's the same thing as the limit as x goes to 3 of x plus 3. Yes, I got it. So here's the thing. Like this process of canceling out factors to evaluate a limit, it works. Okay. So what you can do if you have a rational function, right? When you plug in, if you plug in the limit and you get this 0 divided by 0, okay, this thing called indeterminate form, generally means there's something you can do to evaluate the limit. Okay, there's some method you can do to solve. Okay, so what I'm going to do here now is I'm going to show you a number of methods, a number of trick methods here. All right, using this strategy here. Okay, and so here's what you want to do. Okay, so these are the strategies. All right. So the first thing you want to do is learn to recognize which limits can be evaluated by direct substitution. So literally, if you can, okay, if you can just plug the value in, and it's in the domain, you know, that's the easiest thing you should do. So the first thing you should always try to do is literally just plug it in, okay. So the second thing is when the limit of f of x as x approaches c cannot be evaluated by direct substitution. So what you're going to do is you're going to try to find a function g that agrees with f for all x other than x is equal to c. And then you're going to apply this theorem here, this canceling out method that I've showed you here, to evaluate the limit. All right, so what you're going to do is you're going to try the dividing out technique. That's what we're going to do first, or the rationalizing technique as needed. And I'm going to give you a ton of examples on these. And then if none of that works, what you can do is you can use a graph or table to reinforce your conclusion. But what you're going to see here is all the examples I'm going to show you. It's going to work out very, very nicely. Okay. So let's try first the dividing out method. All right, and so look here. You're going to see how these are going to work. So you're going to have the limit as x goes to 2 of x squared minus 4 divided by x minus 2. So look, if you first apply direct substitution, you would get 2 squared minus 4 over 2 minus 2. You would get 0 over 0. All right, so that's the indeterminate form. Okay, so you're going to see like, what do I do next? So now you're going to try the dividing out, or you can also call it the canceling out. And the key here, what you're going to do is you're going to factor the numerator, right? You look at this and you see that's a difference of 2 squares. So x squared minus 4 is going to factor into x minus 2 over x plus 2 over x minus 2. Now look what happens. They cancel out. And you're left with the limit as x goes to 2 of just x plus 2. So what I'm saying here is this new function, x plus 2, agrees with this x squared minus 4 divided by x minus 2 at everywhere but x is equal to 2. So now you can evaluate the limit literally by just plugging it in. And that's how we got it. So if you have a rational function here, really what you want to do is you just want to factor and cancel out here. Okay. Let's try this one. So the limit as x goes to 3 of, let's look at 2x squared minus 5x minus 3 all over x minus 3. So look, I'll save us some time, but if you were to plug 3 into this, you would get, let's see, even just real quickly, right? Like 3 squared is 9 times 2 is 18, minus 15 minus 3 is 0, and 3 minus 3 is 0. So you get 0 over 0 if you just plug this in. So what you're going to do here, all right, to try the dividing out is you're going to have to factor the numerator. So what I would do is, I would maybe, even pause the video here and see if you can remember how to factor this trinomial. But I'll save us some time, okay, and just show you real quickly, like, look, this is going to factor into 2x plus 1 times x minus 3 over x minus 3. And look, a dead giveaway is when you have this x minus 3 in the denominator, that's probably going to be one of the factors in the numerator, so that should really help you factor it. So these are going to cancel out. You're left with the limit as x goes to 3 of 2x plus 1, which you can literally just plug in. So 2 times 3 is 6 plus 1. That gets you 7. All right, let's try this one. Let's look at the limit as x goes to 0 of x over x squared minus x. So obviously if you plug 0 in, you get 0 divided by 0. So look, hopefully you see it. In the denominator, look, I could factor out an x. So this is the limit as x goes to 0 of x over x times x minus 1. And look what cancels. An x cancels here. So this just becomes the limit as x goes to 0 of 1 over x minus 1. Okay, which you can just directly plug in. So this becomes 1 over 0 minus 1, which is 1 over minus 1, negative 1 here. So it simplifies to just negative 1. So the key here, what you're seeing here is like factoring. is the key step here for dividing out. Okay, if you can factor correctly here, it kind of like just begins to fall into place. All right, let's do two more here. Okay, so again, these are like the dividing out method. So let's take a look at this one here. Let's look at the limit as x goes to 6 of 6 minus x all over x squared minus 36. All right, so again, you know, if you plug 6 in, you get a divide by 0. You end up getting 0 over 0. So there's something you can do, right? So the limit as x goes to 6. This down here is going to factor as x minus 6, x plus 6. So look, you have this 6 minus x. It's like really, really close here. So what you're going to do is you're going to factor out a negative here, right? When you factor out a negative, it becomes x minus 6, right? It literally flips, right? Because if you were to distribute the negative, you'd get back to negative x, and then you get back to positive 6. So you see those cancel. And this is the limit as x goes to 6 of negative 1 over x plus 6. Well, now you can literally plug the 6 in. And this just becomes negative 1/12 here. All right, let's try this tricky one here now, okay? So this is the limit as x goes to 0 of e to the 2x minus 1. So the 2x is the exponent here, all over e to the x minus 1. Well, if you plug 0 in, right, you get 1 minus 1 divided by 1 minus 1. You get 0 divided by 0. So the trick is you need to figure out how to factor this. Well, check this out. I could rewrite this as e to the x squared, right? Because when you power to a power, you multiply. Minus 1. Well, 1 is the same thing as 1 squared. All over e to the x minus 1. Now look, you have the difference of 2 squares in the numerator. So this is the limit as x goes to 0. This is literally going to factor as e to the x minus 1 over e to the x plus 1 divided by e to the x minus 1. Now look what happens. Cancel, cancel. You get the limit as x goes to 0 of e to the x plus 1. So this is e to the 0 plus 1. Well, that's 1 plus 1. That gets me 2. So the trick here, whenever you see this e to the 2x, like remember that it's e to the x quantity squared. So you could factor this as the difference of 2 squares. Okay, I know this lecture is lengthy and there's a lot going on, but we believe it or not, we still actually have a significant amount of work to get through. Okay, so let's now talk about you know, as you go through these videos, right? If you need to pause and take a break, you know, you're absolutely more than welcome to. Okay, don't feel like you have to sit and watch everything in one sitting here. Okay, so we've talked about the dividing out method. So going to the next method, you know, going back just a little bit, we talked about something called the rationalizing technique. So let's look at this one here. Let's look at the limit as x goes to 3. Now this is going to be pretty complicated. The square root of x plus 1, and then outside of the radical minus 2 over x minus 3. Okay. If you were to plug 3 directly in, right, you'd get 3 plus 1 is 4, square root of 4 is 2, 2 minus 2 is 0. Oh, look, 3 minus 3 is 0. You'd get 0 divided by 0, so you get the indeterminate form. So what that means is there's something you can do to solve this. And what you're going to do is you're going to rationalize the numerator, right? So what you're going to do that, you're going to multiply both the top and bottom, the numerator and denominator, by the conjugate of the numerator in this case here. So you're going to multiply by the square root of x plus 1 plus 2. So this now becomes, all right, so when you multiply here, the limit as x goes to 3. I'm going to do the denominator first. Do not distribute here, and you'll see why. X minus 3 times, and then it's the square root of x plus 1 plus 2. Now watch what happens here when you do this. Okay, so you're going to have to FOIL. Square root of x plus 1 times square root of x plus 1 becomes x plus 1, right? Then look, square root of x plus 1 times plus 2, and then minus 2 square roots of x plus 1. The middle terms cancel out, right? Like it's the factored version of the difference of two squares. So the middle terms cancel out. Okay, so that's awesome, right? That was a property we learned of when you multiply conjugates. And then you get minus 2 times plus 2, you get minus 4. So this becomes the limit as x goes to 3. Look, x plus 1 minus 4 becomes x minus 3 divided by x minus 3. Do you see why I didn't distribute? Square root of x plus 1 plus 2. Well, look what's going to cancel here. Cancel, cancel. This becomes the limit as x goes to 3 of 1 all over square root of x plus 1 plus 2. And now you can just plug this in, right? So this becomes 1 divided by the square root of 3 plus 1 plus 2. Well, that's 1 over the square root of 4 plus 2. This is 1 over 2 plus 2. Or we see that it's 1/4. Okay, so the key here, when you see something like this, multiply by the conjugate of the numerator, all right? Or if the radical is in the denominator, you can multiply by the conjugate of the denominator here. And then when you go to FOIL, just remember, okay, I literally go like this, and then just this, because the middle terms are going to cancel out. Okay, that's incredibly important. All right, so what I'm going to do is I'm going to go to the next slide, and what I encourage you to do is pause the video after I put up the problem and try this method, because I'm going to do another one here and see if you can follow through this method. Okay. All right, so here's the next one. Okay, so again, what we're going to do here is another rationalizing technique. So this will be the limit as x goes to 0. And we're going to look at the square root of x plus 6 minus 6. Oh, excuse me, minus the square root of 6. Sorry. So square root of x plus 6 minus the square root of 6 divided by x. And look, you see obviously here that if you plug in 0, you get the square root of 6 minus the square root of 6 is 0 over 0. Okay. All right, so the method here, I'm going to rationalize the numerator. So I'm going to multiply by the square root of x plus 6 plus the square root of 6 divided by, so remember you can only multiply by 1, right? So the square root of x plus 6 plus the square root of 6. All right, so the limit as x goes to 0. Okay, so remember when you FOIL conjugates, you only need to do the f and the l. So square root of x plus 6 times square root of x plus 6, right, becomes the square root of x plus 6 quantity squared, which is just x plus 6. Minus plus becomes minus. and then the square root of 6 times the square root of 6 is 6. All over, remember don't distribute here, x times the square root of x plus 6 plus the square root of 6. Well, look, 6 minus 6, that's just x. So what's going to cancel? Look, the x's cancel. Boom, boom, boom. So you're left with the limit as x goes to 0 of 1 over the square root of x plus 6 plus the square root of 6. So you can now just plug 0 into this, right? This just becomes 1 over the square root of 6 plus the square root of 6, because 0 plus 6 is 6, which is just 1 over 2 square roots of 6. So just the key you're seeing here is multiplied by the conjugate. And then when you go to FOIL, remember the middle terms cancel out. Okay, so the middle terms again cancel when foiling here. Okay, that's the important, one of like the key important things to remember here. All right, let's do one last one. It's just a big algebra problem. Okay, that you'll have to work through here. So this next one here. Let's look at the limit as x goes to 0, and then in parentheses, 1 divided by x plus 4 minus, and then outside of that, 1/4, all divided by x. So look, if you plug 0 in, right, you get 1/4 minus 1/4 is 0 over 0. You get the indeterminate form. So look, I'm going to rewrite this. This is 1 over x plus 4 minus 1/4 over x. So what you're going to do is you're going to combine this, right? So you're going to have to find the LCD of x plus 4 and 4, which is just 4 times x plus 4. Right? That's a college algebra problem there. So this, when I change this, this just becomes 4 over 4 times x plus 4 minus this becomes x plus 4 all over 4x plus 4, and then still divided by x. Well, now look what happens when I combine this, and you have to just be careful with the negative here. You get 4 minus 4, that goes away, and then I'm just left with minus x. So minus x divided by 4. Oh, I forgot the limit part. Don't ever forget the limit. Limit as x goes to 0 of minus x over 4x plus 4 divided by x. So look, if you do keep, change, flip, this becomes the limit as x goes to 0 of minus x over 4x plus 4 times, flip this, 1 over x, the x's cancel, boop, boop, and you become the limit as x goes to 0 of minus 1 over 4 times x plus 4, which you can literally just plug into this now, right? So 0 plus 4 is 4, 4 times 4 is 16, so this becomes minus 1/16. So sometimes when you see these problems, literally what you have to do here is just like work through the algebra, like just boom, 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 blow through the algebra here. So if all other methods fail, okay, try to simplify with algebra. Okay, and maybe it'll work out here. Okay, next I want to show you a theorem called the Squeeze Theorem. All right, it works like this. If h of x is less than f of x less than g of x for all x in an open interval containing c, all right, except possibly at c itself, okay, If you have the limit as x goes to c of h of x is equal to L is equal to the limit as x goes to c of g of x, okay, then that middle limit, okay, all right, here, the limit as x goes to c of f of x exists and is equal to L. So what you're seeing here, look, you have g of x. That's greater than or equal to all the functions. You have h of x, which is less than or equal to the other two functions. And f is between them, okay, for all values. All right. If you have the limit as x goes to c and h and g of x converge to some value, then so does f of x. Okay, that's what the Squeeze Theorem shows us. And what you're going to notice when you read the text, or when I do some proofs later on in the class, I'll say, okay, we'll prove this by the via the Squeeze Theorem. Okay. So let me just show you a visual of this. Okay, so just so you could see. All right. Suppose you have this. Okay. Again, you have h of x is less than or equal to f of x, which is less than or equal to g of x. All right. And I tell you that h of x is 4 minus x squared is less than or equal to some function f of x, which is less than or equal to 4 plus x squared. Okay. And I ask you to find the limit as x goes to 0 of some function f of x. Well, look, what you can do is you can say, okay, well, let me find the limit as x goes to 0 of this 4 minus x squared, which has to be less than or equal to the limit as x goes to 0 of f of x, which has to be less than or equal to the limit as x goes to 0 of 4 plus x squared. Well, look, if you plug 0 into this, you get 4 minus 0, you get 4 is less than or equal to the limit as x goes to 0 of f of x, which must be less than or equal to, if you plug 0 into this, you get 4. So look, the only way this equality holds is that the limit as x goes to 0 of f of x must be equal to 4. And look, you can see it if you look at the graph of this. This is what 4 minus x squared looks like. This is h of x. G of x is 4 plus x squared, so it looks like this. So look, if f of x is always bounded between that, if this is f of x, we don't even know what it is, but what we're saying, we're squeezing the limit by these inequality, and we see that limit of f of x as x goes to 0 is the same thing as the limit as x goes to 0 of these two functions here. All right, so the Squeeze theorem is just a theorem that we'll use, in the coming lectures to help us do some proofs. Okay. All right, let's look at let's now look at some special trig limits. Okay. And I'm going to prove one of these for you here. Okay, so these are 3 special trig limits that come up, or 3 special limits. The last one is not a trig limit, but so if you have the limit as x goes to 0 of sine of x over x, you'll notice that you get 0 over 0 when you plug that in. So it turns out that limit as x goes to 0 of sine of x over x is equal to 1. Okay, and the proof of this is in the text. Next, if you have the limit as x goes to 0 of 1 minus cosine of x over x, like if you were to plug 0 in, you'd get 1 minus cosine of 0. So that's 1 minus 1 is 0 over 0. So you get that indeterminate form. So it turns out that this limit is equal to 0. All right, I'm going to prove this to you over here. I'll prove it in a second. And then next, if you have the limit as x goes to 0 of 1 plus x raised to the 1 divided by x, okay, notice you get a 1 divided by 0 here. Okay, it turns out that this is the number e. Okay, so whenever you see this limit, it's just e. All right, so here's the proof of this one right here. I'm going to just do it with some simple algebra. Or some special algebra and trig identities. This is 1 minus cosine of x all over x. Okay, so to prove this limit, the trick is here, you multiply the numerator and denominator by the conjugate of the numerator here, which would be 1 plus cosine of x. Well, when you distribute here, okay, you get the limit as x goes to 0. Remember, in the conjugates, the middle part cancels out, right? The two middle terms. So when you FOIL the conjugate, so you get 1 times 1 is 1. And then minus cosine of x times cosine of x gets me minus cosine squared of x. All over, well, I have x, 1 plus cosine of x. Okay, so what you do next here is you have to remember a trig identity here. Okay, if you look back, I'm going to go back real quickly in the slides here. If you remember this one right here, okay. So this one right here, what it was telling us, look, I had 1 minus cosine of x. So what I'm seeing here is that sine squared of x is equal to 1 minus cosine squared of x. So when I go back in to prove that problem, I can replace the numerator here by sine squared of x. What I can then do next is sine squared of x is the same thing as sine of x times sine of x. What I can then do next is I can break this up, right? So I can go the limit as x goes to 0 of, I'm going to like peel this apart. I'm going to write this as sine of x over x times sine of x over 1 plus cosine of x. And then using our properties of limits, what I can do is I can evaluate this, because we're going to see both these limits exist, is I can write this as the limit as x goes to 0 of sine of x over x times the limit as x goes to 0 of sine of x over 1 plus cosine of x. Well, look, here what we see, limit as x goes to 0 of sine of x over x, that's this limit right here. That's equal to 1. And I can actually plug 0 into this. So if I get sine of 0 is 0, over 1 plus cosine of 0 is 1, so this becomes 0 over 1 plus 1. Well, this 0 over 2 is 0, so this just becomes 1 times 0. We see that this limit is equal to 0, which we see right here. Okay. So what we want to do now is we want to use these special trig limits to evaluate some limits. Like so let's see if we can use some of these tricks here, some of these special limits to evaluate some trig limits. Okay, so this is some examples with some special limits. All right, so let's look at this first one here. Let's look at the limit as x goes to 0 of sine of x over 5x. All right, well, notice this, like, it kind of looks like the sine of x over x, but I have this 5 down here. Well, this 5 is literally just a constant, right? So I could factor it out as 1/5 and find the limit as x goes to 0 of sine of x over x. Well, check this out. The limit as x goes to 0 of sine of x is just 1. So this is 1/5 times 1, which is 1/5. All right, let's try this one here. Let's look at the limit as theta goes to 0 of cosine of theta times tangent of theta all over theta. Well, you'll see here if you just plug 0 in for theta, you get cosine of 0, which is 1, times tangent of 0, which is 0, divided by 0. So you get 0 over 0. So what you're going to want to do, right, is so, okay, like what can I do here? Okay, so like what is tangent equal to? So if you have to, you can go back to this right here. Okay, so tangent is sine over cosine, right? Sine over cosine. So this becomes the limit as theta goes to 0 of cosine of theta times sine of theta over cosine of theta all over theta. And like, look what happens here. The cosines cancel, cancel, and you're left with the limit as theta goes to 0 of sine of theta over theta. Well, look, that's instead of x here, I just have theta. So this just goes to 1. All right, let's try. Let me get some space here. Actually, let me get some space and go to the next slide here. Okay, so again, this will be special limits here. Let's look at the limit as x goes to 0 of tangent squared of x all over x. Okay, so for this one here, like you plug in 0, right? Tangent of 0 is 0 divided by 0. You get that 0 over 0, so that indeterminate form. Okay, so let's try. So this becomes the limit as x goes to 0, tangent, right? So tangent squared is the same thing as sine squared of x over cosine squared of x divided by x. So how are you going to solve this, right? So you go keep, change, flip, right? So you keep this, so it's the limit as x goes to 0 of sine squared of x over cosine squared of x times, and then you flip this, 1 over x. All right, so look what happens now. Now you're going to kind of do this same thing I did here, where you're going to peel it apart, right? So like notice how it's like, oh, I know what sine of x over x is. So let me write this as the limit as x goes to 0 of sine of x over x times, and then don't forget I still have a sine of x left, sine of x over cosine squared of x. Well, the limit as x goes to 0 of sine of x over x. Boom, that's 1. Sine of 0 is 0 divided by 1 here. Gets me 0. So this limit here is just 0. All right, now let's take a look at this complicated, crazy one here. Let's look at the limit as t goes to 0 of sine of 3t all divided by 2t. Okay, so notice here, all right, this is the important thing. This right here says sine of x over x is equal to 1, okay? So really what's important here is that what's inside the sine function and what's in the denominator are the same. They're the same. Okay, they're x. So here's the important thing. If this had been like 5x over 5x, boom, it's still equal to 1. Okay, they need to be the same. Okay. So when you look at this, I have 3t and I have 2t down here. It's like shucks. Okay. So I'm gonna the 2 doesn't help me, so I'm gonna factor that out. So here's the thing. I have a 3t here. I want to have a 3t down here. So if I'm going to put a 3 here, okay, I can maintain equality by also putting a 3 up here because they'll cancel out here. Okay. So, now check this out. Now this 3 I'm going to factor out. So this becomes 3/2 the limit as t goes to 0 of sine of 3t all over 3t. Now notice this right here. Okay, if I just do a change of variables, let's let x equal 3t. Well, here's the thing. As t goes to 0, 3t goes to 0, and x also goes to 0. So I could even rewrite this next as the limit as the 3/2 times the limit as x goes to 0 of sine of x over x. But if this seems confusing to you, what you can just remember as long as the what's inside the sine function and what's in the denominator is the same, then it still equals 1. So this becomes 3/2 times 1. So this is 3/2. So the trick was here being like, look, I had a 3 in here. I have to put a 3 down here. But to put a 3 down here, I also have to put a 3 in the numerator as well. Okay. Let's do one last problem for our lecture here. So we have a lot going on here. Okay. So here's the last problem. We made it through the lecture here. Let's look at the limit as x goes to 0 of cosine of x minus sine of x minus 1 all over 2x. So it's like, how do I solve this? If you plug 0 in, you get 1 minus 0 minus 1 is 0. 2 times 0 is 0. So you get 0 over 0. You get the indeterminate form. Okay, not great. Great actually, because that means you can solve it. So the key here is you want to break this up. All right, so I'm going to write this as the limit as x goes to 0. Look, I'm going to take this minus sine of x over 2x. I'm going to break that apart here. Plus cosine of x minus 1 all over 2x. Okay, so it's the limit of all of this. Now let me go back. This really, really looks like, check this out. It looks very close to just sine of x over x. This one looks familiar. Cosine of x minus 1. I need it to be 1 minus cosine of x. So here's what I'm going to do. I'm going to break this up as two different limits. Limit as x goes to 0 of sine of x over 2x plus the limit as x goes to 0 of cosine of x minus 1 over 2x. Well, look, let me factor out negative 1/2 here. So minus 1/2, this becomes the limit as x goes to 0. So when I factor out a negative 1/2, look what I'm just left with. I'm left with sine of x over x. That's great. That's awesome. Okay. Now here, okay, to flip this around, to have this be 1 minus cosine of x, I'm going to factor out a negative and then also factor out this 2. So this becomes minus 1/2. Limit as x goes to 0. When I factor out a negative, this becomes 1 minus cosine of x over x. Check this out. Look, sine of x over x, what is that? That's just 1. 1 minus cosine of x over x is 0. So this becomes minus 1/2 times 0. Or excuse me, times 1, sorry. Minus 1/2 times 0. Right, going back. Sorry, I had a little confusion there. So this just becomes minus 1/2 minus 0, which is minus 1/2. All right, class. I know this was an incredibly long lecture, and there was a ton to see and learn in here. But the key takeaways are the following. If you can plug it in to evaluate, just plug it in. Okay, then you're going to have to try the dividing out, the factoring method I talked about, then the rationalizing. If that doesn't work, the rationalizing method. And then there's all these trig limits. So when you go do your homework, you're going to get an opportunity to practice. And the more you practice, the easier and easier these will become.